Alright, ladies, this lecture video covers Chapter 17. Chapter 17 is on redox reactions, so oxidation and reduction reactions. So we'll talk about what that means in a moment, but first we need to talk about oxidation numbers. So we've seen oxidation numbers quite a bit already, but we haven't actually put necessarily that name to it. So our oxidation numbers are the ions that our elements are typically going to form in solution. So your actual definition is a description of electrons lost or gained by an atom. So for example, sodium is going to form a positive 1 cation always. Fluorine's going to form a negative 1 anion. Magnesium is a positive 2. So these are the oxidations. So sodium's is a positive 1, oxidation number. Fluorine's is a negative 1, and then magnesium is a positive 2. So we have a few rules that we are going to be looking at in order to determine oxidation numbers. We're going to have to calculate them most of the time. So rule number 1, oxidation numbers for any element in its elemental state. So typically when it's by itself, is going to be 0. So sodium by itself, it's neutral, it's 0. Oxygen is diatomic. When it's diatomic, it's 0 oxidation number. Phosphorus, it shows up in groups of 4 when it's by itself, so its oxidation number is 0 as well. Sulfur shows up as S8. Sulfur's is 0 as well. So elemental state is 0. Oxidation, rule number 2, oxidation number for an element is existing as a monoatomic ion is the ionic charge. So like what we were talking about here. So sodium is a positive 1, oxidation number, fluorine, negative 1. And the charges tell us what the oxidation number is. Rule number 3, oxygen has an oxidation number of negative 2 except in peroxides. So these are compounds with O2 that have a negative 2 charge. So each of those oxygens has an oxidation number of negative 1 at that point to total to that negative 2. So our example here is magnesium oxide. So magnesium is going to form a positive 2 like we were talking about here. And in order to cancel that positive 2 out, oxygen's oxidation number is a negative 2. But here with sodium or NaO2, sodium has a positive 1 charge that it forms, and there's 2 of them. So overall, we have a positive 2 charge. There's 2 oxygens, and they each have some negative charge that has to cancel out that negative or that positive 2 with a negative 2. So each of those oxygen has to have a negative 1 charge. So 2 times a negative 2 is, or 2 times a negative 1 equals a negative 2. To cancel out that positive 1. So this is a peroxide, sodium peroxide. Rule number 4, hydrogen has an oxidation number of positive 1 unless it's combined with metals, at which point it would have an oxidation number of negative 1. So here with carbon, carbon is not a metal, so hydrogen is going to have a positive charge. There's 4 hydrogens. They each have a positive 1 charge, so overall we have a positive 4 charge for our hydrogens. That carbon, in order to cancel out that positive 4 charge, has to have a negative 4 oxidation number. So that's what we're looking at here with CH4, with methane. Rule number 5, in molecular compounds, so molecular compounds are nonmetals attached to each other. The more electronegative element has an oxidation number equal to its normal anion charge, so the charges that we typically assign to them. Fluorine is our most electronegative element. So fluorine is most electronegative. Oxygen is our next most, and we're increasing electronegativity as we go left to right on the periodic table, and then bottom up. So we're doing a diagonal up to where fluorine is for electronegativity. So the most electronegative element keeps its normal charge. Fluorine's always going to be negative 1 if it's in a molecular compound. Oxygen's typically going to be negative 2 unless it's attached to a fluorine. Rule number 6, the sum of all oxidation numbers for all atoms or ions in a compound is equal to 0. With compounds, we want them to be neutral. So not typically, if a neutral compound, our oxidation numbers are always going to equal to 0 for a neutral compound. And then rule number 7, the sum of oxidation numbers for polyatomic ions are equal to the ionic charge. So here our example is carbonate ion. So the carbon and the 3 oxygens, all their oxidation numbers are going to add up to a -2. So with example number 1, we're going to practice using these guys. So example number 1, assign an oxidation number to each atom in the following. So our first one that we're looking at is Br2. So bromine, if it's by itself, it's going to show up as diatomic. So that means that we have an oxidation number there of 0 because it's in its elemental state. Diatomic is considered elemental. Okay, our next one that we're looking at is potassium. So it says K plus, so K plus 1. That's its oxidation state. The charge is its oxidation state. Our next one that we're looking at is lithium and fluorine. So here we have to do a little bit of calculations, but we can easily just do it in our head. Lithium's always going to form a +1 charge. So lithium's oxidation number is +1. And fluorine, in order to cancel that out, is going to be -1. So we just want a neutral compound, so they have to add up to 0. We have CO2, carbon dioxide. So oxygen is more electronegative than carbon is. It's closer to fluorine. So oxygen gets to keep its -2 charge. There are 2 of them. So overall on the oxygens, we have a -4 charge. The oxidation number on one oxygen is -2 though. But we need that -4 in order to determine carbons, which needs to neutralize the negative charge from the oxygens. So carbon has to be a +4. So we're just doing a little bit of math here to figure out what carbons is. And these, the pink writings that I have up here are the rules that I was looking at for those. So here we have sulfur and oxygen. Those are 2 nonmetals, so we're looking at rule number 5 with molecular compounds, and then rule number 7 because it's the polyatomic ion. So oxygen is more electronegative than sulfur, so oxygen gets to keep its -2 oxidation number. There are 4 of them from our subscript, so overall we have a -8 charge. We need to figure out what sulfur's is, but we have to keep in mind this -2 charge overall. For our polyatomic ion. So technically what we're doing is we have a -8 charge from our oxygens. We have some positive charge from our sulfur, and that has to equal a total charge of a -2. So obviously this sulfur's charge has to be a +6. So -8 + 6 is going to be a -2. And the last one that we're looking at, so we are looking at Na2O2, which we did up above here, but sodium's always going to have a +1 charge. So overall, with our 2 sodiums, we have a +2 charge. So +1 oxidation number, overall +2 charge that needs to be canceled out by our 2 oxygens. So we have 2 oxygens, they each have some charge, and it's a -1 oxidation number to cancel out that +1 charge there. So we're just doing like a little bit of math like we did down here. All right, example number 2. Calculate the oxidation number for carbon in each of the following compounds. We need, if it's in a compound, we need to figure out what the other guys are in order to figure out what carbons is. So technically, we'd be looking for all of them. Diamond, carbon, it's not diatomic. It shows up just as a single atom in its elemental state. So our oxidation number is 0. So for marble, which is calcium carbonate, we got to do a little bit of math here. So calcium is in group 2A, so it's always going to form a +2 charge, so +2 is its oxidation number. Carbon, we got to figure that out, but we have to look at oxygen first because it's the more electronegative element, going back to rule number 5. So it gets to keep its -2 typical charge. There are 3 of them. So we're doing 3 times its -2 oxidation number is going to give us a total -6 charge. And we have a neutral compound. So that +2 and -6 plus carbon's oxidation number needs to equal to 0. So we have a +2 plus some positive charge minus 6 has to be 0, and that ends up, this question mark ends up being a +4 for carbon there. We do something very similar with baking soda, NaHCO3, sodium bicarbonate. Sodium has a +1 charge. Always, it's in group 1A. Hydrogen, we're not sure necessarily what it is, but here it's attached to nonmetals, so it's going to be a positive charge with the bicarbonate ion. We already had calculated the CO3 earlier, so that's the -2 oxidation number for oxygen, total of a -6. So the +1 +1, this has to be a +4 in order to cancel out that -6 to get a neutral compound. So here, our oxidation numbers for carbon were 0, +4, +4. I will post the answers for example number 3 and 4 as like a separate page on Canvas. We're not necessarily going to go through them right now. But there's more practice for you there if you want to try it. And then check your answers with that assignment. Okay, so the next thing that we're looking at is actually like our oxidation reduction reactions. So an oxidation reduction reaction, typically abbreviated to redox reaction, is a chemical change that involves the transfer of electrons. So basically what we're talking about is where are our electrons coming from, where are they going? And electrons are coming from somewhere and going to something. So redox, oxidation, reduction are always coupled together. Okay, so oxidation. Oxidation is our loss of electrons or an increase in oxidation number. And our reduction is a gain of electrons or a decrease in oxidation number. Probably your easiest way to remember the difference between oxidation and reduction is this little saying, Leo the lion says grr. So the Leo part, if we're losing electrons, we're oxidation. If we're gaining electrons, we're reduction. So Leo the lion says grr, or just Leo says grr, but I think the lion is pretty cute. Okay. We also need to talk about oxidizing agents and reducing agents. So our oxidizing agent is the substance being reduced. So think about it like they're opposite there. And our reducing agent is the substance being oxidized. It causes the reduction of the other guy by giving away its electron. The oxidizing agent is a substance being reduced, is accepting electrons, causing the oxidation of the other guy. Okay, so exercise number 5. We talked about that a little bit a few seconds ago, but the electrons are moving from one thing to another thing. So that's why they're always coupled together. So oxidation, we are losing electrons, and then reduction, we're gaining those electrons. Okay, let's look at exercise number 6. So for each of the following reactions, identify the substance being oxidized and the substance being reduced. Then identify the oxidizing agent and reducing agent. Okay, so the first thing we need to do is we need to figure out the charges on our atoms here, and we're going to compare them in our reactants to our products. So we need to look at our products to figure out if we're gaining or losing electrons, but if we're talking about oxidizing, reduced, whatever, we're really just talking about our reactants. So chlorine is diatomic. It's in its elemental state, so its oxidation number is 0. Iron is in its elemental state by itself. Its oxidation number is 0. So here with iron to chloride, chlorine has a -1 charge if it's attached to a metal, especially. And there's 2 of them, so overall we have a -2 charge for our chlorines. But 1 chlorine has an oxidation number of -1. Iron, in order to cancel out that -2, has to have a +2 charge for iron. So we have to look at our oxidation numbers in order to figure out if something is oxidized or reduced. So notice here, let's compare chlorine. So here we're starting with 0 and ending up with an oxidation number of -1 for just 1 chlorine. So we are gaining electrons. So we are being reduced. So reduced. Here iron is losing electrons to form a +2 charge, so it's being oxidized. So our oxidizing agent and reducing agent, those are opposite of what we would, their name is. So the one being reduced is the oxidizing agent, and the oxidized reactant is our reducing agent. For letter B, again, we have to look at our charges. So here zinc has it's in its elemental state, so it's got an oxidation number of 0. Iron, it tells us here in its charge, is a +2. Zinc in the product is forming a +2 charge, and then iron is 0 at that point. So compared from your reactants to your products, zinc is losing 2 electrons to form a +2. So Leo the line says grr, oxidation is losing electrons. And then for our iron, we are gaining electrons from going a positive to a neutral charge. So it's being reduced. And likewise, our zinc is our reducing agent. Iron +2 is our oxidizing agent. Exercise number 7, we're only going to go through letter A in this video. I will post the answers for B and C in that same assignment that I'm doing example 3 and 4 in. So exercise number 7, we're doing the same thing, but I wanted to go through letter A because we are dealing with, we don't have metals in there. Metals are typically our easiest ones to figure out for redox reactions, but we're going to see only nonmetals as well. So let's look at the charges of what we have going here. So we have carbon monoxide. So oxygen is more electronegative, so it's going to have that -2 charge already established. And carbon's oxidation number is going to be a +2 to cancel that out. Oxygen gas here is 0. We're not going to, never mind. Okay, and then let's look at carbon in the products. So carbon in the products, we have to figure out oxygen first because it's more electronegative. So 2 oxygens with a -2 oxidation number is going to give us an overall negative charge of -4. That means carbon has to have a +4 charge there. So notice that carbon, we are losing electrons in that sense to get to from a +2 to a +4. And then our oxygen is gaining electrons there. So that means that our carbon monoxide, that's our oxidizing agent, because carbon is losing electrons. And then, it's being oxidized, not our oxidizing agent. It's our reducing agent. And then oxygen gas is being reduced in order to form carbon dioxide gas. So carbon is our reducing agent, and then oxygen gas is our oxidizing agent. Again, look at B and C for the work on that. Or you can look at it here, whatever. But with example 3 and 4. Okay, the next thing that we're going to talk about are spontaneous redox reactions and predicting if something is favorable or non-favorable. So spontaneous or non-spontaneous. So our spontaneous reactions are redox reactions that occur without any input of electrical energy. So we don't have to put any energy in. It happens on its own. So it's spontaneous. doesn't require energy. Reduction potentials. This is a tendency for substances to gain electrons and undergo reduction. So typically we're going to measure these in electron volts, but we're not necessarily going to cover that in this chapter. But if you went on to higher chemistry, you would be talking about reduction potentials as well. Okay, so we're going to be looking at the activity series of metals in order to predict if a reaction is spontaneous or not. So let's look at this table 16.1. So at the top with lithium, these are our most reactive elements. So the higher up we go, they're most reactive, they're most easily oxidized, so they want to lose electrons. And the strongest tendency to lose electrons, that's what oxidize means. Towards the bottom with gold, these are least reactive, most difficult to oxidize, and least tendency to lose electrons. So these guys want to be reduced. They want to be reduced. These guys want to be oxidized. So we need to look at this chart in order to figure out if a reaction is spontaneous or non-spontaneous based on where they are on this spectrum here. Okay, predict whether the following reaction is spontaneous or non-spontaneous. So let's look at the specific reactions. So here I have the half reactions written down, but you can also do what we were doing earlier. So nickel here, its oxidation number is a +2, tin's is 0, nickel over here is 0, and then tin here is a +2. So from this nickel to that nickel, we're gaining 2 electrons. That's what this half reaction means. We're gaining 2 electrons to get to nickel here. Tin, we're starting with a 0 oxidation number and then going to a +2, so we're technically losing electrons at that point. Okay, so if we're losing the electrons, that means we are oxidized, and if we're gaining electrons, we are reduced. But tin is being oxidized here, and it's closer to the bottom, so it actually wants to be reduced. So nickel is closer to the top, and it wants to be oxidized. So this is the opposite of what they want to do based on this activity series. So this is going to be a non-spontaneous reaction. It's opposite of what they want to do. Nickel wants to be oxidized, and tin wants to be reduced, but they're opposite here for this problem. So it's non-spontaneous. It's not going to occur unless we make it. And then we will talk about that here with spontaneous and non-spontaneous reactions. So we're going to talk a little bit about batteries. So batteries are an electrochemical cell, and they create an electrical current from a redox reaction. So basically what they're doing is they are harnessing that movement of electrons using the anode and the cathode for the battery. So anode is the negative charge, so that's where the oxidation has occurred, where we have electrons leaving, and then our cathode is the one that is accepting the electrons, and it's causing the reduction of the substance in the battery on the cathode end. So we have galvanic or voltaic cells. These guys spontaneously produce an electrical current. So we have a redox reaction going on inside a battery that is producing this electrical current, and we're just harnessing that movement of electrons. So electricity is just a movement, a current of electrons. So we are taking that spontaneously or spontaneous redox reaction, and we're just stealing some of its electron to do work for us. So that is how a battery works there. There are also non-spontaneous redox reactions. So this, we're looking at electrolysis. So it's the reverse of a spontaneous reaction, non-spontaneous, obviously. And it uses electricity to do chemistry. So this is where we're putting in work in order to drive a non-spontaneous reaction. So like the nickel and tin that we were looking at in exercise number 9. So an electrolytic cell is it's caused by an electrical current that's driving a non-spontaneous redox reaction. So we are putting an electrical current into this electrolytic cell, which is causing this unfavorable non-spontaneous redox reaction to occur. Okay, so let's talk a little bit about undesirable redox reactions. So corrosion. Corrosion is the oxidation of metals. It is what causes rust to form on our metals, and rust or oxidation of our metals, corrosion, makes our metals really brittle. So they start flaking away, that's typically what our rust is, and eating away at our metal until they're just so brittle and they really can snap easily. So a lot of our buildings, like our structures, are made out of metal. So we really don't want our buildings to rust and to just get really brittle and collapse. So there's one thing that we can do in particular, and that's what we're looking at with example number 7. So example number 7, which of the following metals, if coated onto iron, would prevent the corrosion of iron? So we're looking at zinc, tin, or manganese. So basically what we're doing is we are making these metals into like paint, basically, that we're just going to coat onto our iron bar or whatever in order to stop a corrosion. So let's look at the activity series for these 3 metals relative to iron. So iron is here towards like the middle-ish. And we are looking at zinc. So zinc is up above. Zinc is more reactive than iron is. So it's more easily oxidized. Which means if we coated zinc onto iron, it would, the zinc is the one that would get oxidized before iron. That will help the corrosion of iron for a bit, but after all the zinc has been corroded, we then have iron being eaten away again underneath. So yes, if we coated zinc onto iron, it would solve our issue for a short time, but we're looking for more of a long-term solution. So let's look at tin. So tin is below iron, so it's less reactive and less easily oxidized, so more difficult to oxidize. Which means if we coated iron with tin, the process of it being oxidized is a lot longer, maybe not a lot, but it's longer than iron. So that's a longer term fix than if we were to coat it with zinc, which would be eaten away quickly and then reveal the iron underneath. So tin is going to take longer to oxidize. So that's a better fix to coat on iron than zinc is. Our last one that we're looking at is manganese. So manganese is up here above zinc. So yes, again, it would be a short-term fix, but it's going to get eaten away, corroded a lot faster than zinc would, and then it would just reveal the iron underneath to be eaten away. So tin is our best bet for our longer-term fix. So that is the end of chapter 17. So if you want to practice with oxidation numbers and redox reactions, and then check your answers on the file that I am going to post into Canvas, I would suggest doing that.